Hi everyone. Today what I would like to do in this video is to go in depth over our linked list to visualize how the compiler dynamically and uniquely allocates nodes in the memory. We will also visualize how we add a node to the end of the linked list in constant time, as well as how we delete or insert a node and how to traverse over the linked list. So with that being said, let's get started. What I would like you to pay attention to are the three errors up to the right. One, the current line error is the line we are executing right now. Two, the previous line error is the line where the current line error was at. Three, the waiting line error is the line when we call a function and we are done executing that function, then we should go back to where that function was called and continue executing from there. Here we have two classes, class node and class linked list. So let's see how the compiler dynamically and uniquely allocate nodes in the memory. Now let's take a look at the error, the red error. And then now we will dynamically and uniquely allocate an object in the memory that is a type of the class linked list and assign that address to the pointer named L that is a type of the class linked list. Next, and that's how we see it dynamically. Next, we go to the next line and then we get inside the for loop and we call the function push node. Then when we're done executing the function push node, we go back where that function was called. So let's see that. As you can see, the box blue, it's a nice way to see the local variables that inside the push node. And we pass a value, that is equal to 1. In this line, we will see how we dynamically and uniquely allocate node that is a type of the class node and assign that address to the pointer variable named new node that is a type of the class node. And watch right now, a red box will appear where the pointer new node points to the node that we dynamically and uniquely allocating right now. And it has a value that equals to 1. And there it is. In this line, what we are saying is, if not self.head, if you look at the bottom and you see the box that contains self.head equals none and self.tail is equal to none. So what we are saying, if self.head, go ahead and dereference and access the field self.head and give me what's inside there. If the address is equal to none, which evaluates to false, go ahead and convert that to true and go inside the if statement. And then at that line, we say, give me what new node is pointing to, or what the address new node contains, and dereference and access the field.head and assign the address new node to the field.head. And watch in the box at the bottom, self.head will point to where new node is pointing to. There it is. And next line. We get out, and then now we are pointing to self.tail. That's where we are. That's the line we're executing right now. And we're saying, go ahead and dereference and access the field tail and assign that field the address new node. So now self.tail will be pointing exactly where the new node is. And that's how we maintain constant time when we add a node to the end of the linked list. Every time we add a node to the end of the linked list, self.tail will point to that node at the end of the linked list to maintain constant time. We go to the next line, and then once we return, we exit out of the function, all the local variables will disappear, and you'll see the blue box will go away. Then we go back where the push node function was called. which is inside the for loop. Since there's nothing after the push node function, we just go back to the for loop. Now we are there where the red arrow is. We go down, we call the function again, we pass a value 2, and then we start from the top. And then here, again, we dynamically and uniquely allocating a node that is a type of the class node. And we are assigning that address to the pointer named new node that is a type of the class node. And watch right now, 2 boxes will appear. A box that contains the pointer new node that points to the node that contains a value 2. And there it is. And we're saying at this line, if not self.head, meaning go ahead and dereference access the field.head and see if the address there is equal to none. If in this case, the address is not equal to none because it's pointing to the node that contains an element with a value of 1. So we don't go inside, we go outside the else statement. And what we are saying here, go ahead and dereference to dot tail, which is right now is pointing to the node that contains the element 1, and access the field .next. So what happens when we dereference to dot tail first, it gives us back the address of the node where the element 1 is inside that node. So now what do we say? Dereference to the field .next, dereference to the fields .next, and assign that field .next to the new node pointer that we just allocated. So now the field in the node that contains the element 1 will point to the new node that contains element 2. And there it is. Now, as I mentioned earlier, every time we add a node to the end of the linked list, self.tail, the field will point to that node we add to the end of the linked list to maintain constant time. And there it is. Now self.tail point to the node that contains the element 2. And we get out of the function, everything disappear, all the local variables disappear from that function, and you will see new node, the pointer named new node will disappear, and the box blue will go away. And we go back, and then we do the same thing. We call the function push node again, we pass 3. And here we dynamically and uniquely allocate node that is a type of the class node, and we assign it to the pointer new node that is a type of the class node. And we check if not self.head. Self.head, if you can see, it's pointing to a node which does not equal to none. And then so we don't go inside, we go into the else, and what do we see? Go ahead and dereference self.next. Go ahead and dereference to self.tail and access the field self.tail, and that would bring me an address. And what I'm saying, go ahead inside of that field, assign where the new node we allocated that contains an element 3. Assign the field next to that node, and you'll see right now, as you can see right now, self.next is equal to none. Now we are going to point self.next to point it to the node that contains the element 3. There it is. And now, as I mentioned again, self.tail will point to the node that contains element 3. And we get out of the function, we go back, and we do the same thing. Now we get the process dynamically allocating a node. We check, and then we assign the node that contains the element 3 to the new node. Then we go down, we return, and we continue doing the same thing. We call the function, which is the last time we call the push function. We dynamically and uniquely allocate a node that is a type of the class node, and we assign it to the pointer named new node that is a type of the class node. We check, in this case, self.head does not contain an address that is equal to none. So we go inside the else statement, we do the same thing. Now the node that contains element 4, the field inside there, .next, will point to the node that contains element 5. And then self.tail again point to the last node we added to the end of the linked list. And then we get out of the function. And we go back where the push node function was called. And in this case, now we are at that line. Since there's nothing we can do, we go down, and here we call the function named insert node by position, and we pass an element 2.5 and a position 5. So now we're going to add a node after the node that contains element 4. So let's see that. And inside this function, we are calling another function, which is search node, and pass position, which is in this case 5. What I want you to pay attention here is the new error that I created. It's called second waiting line, is the error where we call the search node function from the function insert node by position. Now, the reason why I did this is because I want you to see, once we're done from the search node function, we go back where that function was called, which is in this case inside the insert node by position. So let's focus on the search node. We say in this line, we say if not self.head. In this case, as you can see, self.head is actually pointing to a node, so we don't get in there. Now we declare a pointer that is a type of the class node, which we do reference and access the field head. Now node will be pointing exactly where self.head is pointing to. And then we declare another variable that is a type of integer, and we assign 1 to it. And watching the blue box, we have 2 variables. It's a nice way to see all the local variables within this function. You have a counter that equals to 1. Now we say while counter plus 1. In this case, counter is 1. So while 1 plus 1, which is 2, is not equal to position. In this case, yeah, that's true. So 2 is not equal to 5. And node.next, yes, node.next, if we look, contains a pointer that does not equal to none. So we get inside, and that's how we right now traverse the linked list. Now we reassign the pointer node to a pointer node with an address that is not equal to none, which is an address that where the node that contains element 2. So now if you notice, the box where the variable node will point to the node that contains element 2. There it is. Now we increment by 1. We do the same thing. 2 plus 1 is 3 is not equal to position, and node.next contains an address that points to another node. So we get inside. Now we reassign the node, the pointer node to the pointer node with an address that does not equal to null, which points to the node that contains element 3. And again, that's how we traverse the linked list. Now we are pointing to the node that contains the element 3. We increment by 1. We do the same thing. And now we assign, we traverse, where we increment by 1, we go back to the beginning of the while loop, and we say counter plus 1. In this case, counter is equal to 4. So 4 plus 1 is 5. Is 5 not equal to 5? That's not true. So the compiler does not bother checking the next, which is node.next. It does not go inside the while loop. Continues at the line after that. In this case, if not node.next, which is not true in this case, node.next actually point to a node that contains element 5. So we don't go inside here. We go to the next line. Now at this line, we return, and all the local variables go away, and then we go back where the search node function was called, which is in this case inside the insert node by position. And here we are, and we check if instance node string. What we are saying, if the variable node or the pointer named node contains a value that is a type of string. If it's that the case, go inside, but in this case it's not, so we go to the next line. At this line, we dynamically and uniquely allocating a node that is the type of the class node, and we are assigning the address to the pointer named new node that is a type of class node. And you will see two boxes appear at the bottom. There it is, the box that contains the pointer and new node that points to the node and points to the node that has a value 2.5 and a field equals to none. And we say at this line, if position is less than or equal to 1. In this case, position is 5, so we don't go inside this F statement. We continue to the next line. If not node.next, what do you think? If we look at the box that has the pointer node, and if we follow the pointer all the way down, and that pointer is pointing to a node that contains the element 4, and we are saying node.next, go ahead and access the field .next. Does that field contain a pointer equal to none? No, it's not. It does not. It points to actually a node that contains the element 5. So we don't go in here. So it evaluates to true, and then we convert it to false. So we don't go inside. We go to the next line. Now, watching this line, watch how we set the field to point to where node.next is pointing to. So if we look at the box where the pointer named node is inside, we follow the arrow, which is we are pointing at the node that contains the element 4, and we are saying, okay, give me the field .next. What is the address in there? Give me that and assign it to the node, which if you look at the box, if you look inside the box where new node is pointing to, and follow the arrow and access the field .next that contains the element 2.5, point to where the node 4 is pointing to. Now, both of these nodes are pointing exactly to the same node. And the reason why is because that's the position we want to insert the node at. So then the line, if you take a look at the arrow, the red arrow, now what we are going to do, we're saying, go ahead and dereference node.next and assign it to point to the new node that contains 2.5, the element 2.5. And that's how we insert a node at position 5. So if you count node 1, 2, 3, 4, and now the node that contains element 4 is pointing to the node that contains element 2.5, and that node that contains 2.5 is pointing to the last node. And at this line, we return, all the local variables go away, and then we go back to where the insert node by position was called. Now we want to delete a position, or we want to delete a position. We want to delete a node by giving a position. So we call the del node by position, and we answer, we pass the position that we want. As you can see, we saw this. We will call the search node, and we want to go back again when we've done executing the search node. We want to go back where that search node function was called from the del node by position function. So now let's focus on the search node function. If now self.head, again, self.head contains points to a node, and we declare a pointer that is a type of class node, which is in this case now the pointer named node, and the self.head will be pointing exactly the same to the same node. And then we have a counter. We do the same thing. We get inside the loop, and then we go back to the loop. We go back, excuse me, to the beginning of the loop. We say counter plus 1. And the value, if we look at the counter is equal to 2, and 2 plus 1 is 3, and 3 is not equal to 3. That's not true. So we don't go inside, then we check if not node.next. In this case, if we take a look at the box that contains the pointer named node, and if we follow that error, the self.next contain an address, which is in this case, it does not evaluate to true. So we go to the next line and we return. So all the local variables go away again, and we go back where the search node function was called, which is in this case in the del node by position function. And we continue from that line. We saw the same thing. If the value inside the pointer node is a type of string, let's go ahead and end the function from there. But in this case, it's not. If the position is less than or equal to 1, in this case, the position is actually 3, which is larger than 1. So we don't go inside. We go to the next line. If not, node.next.next. So if we follow the error where inside the box, the node, the pointer named node inside that box, if we follow the error and we go there, which is the node that contains element 2, and we say go ahead and follow the .next error, which we go to the next node, which is the node that contains element 3, and we say follow the self.next. Does the field self.next contain an address that is equal to none? That's not true, because it's pointing to a node that contains element 4. So we go down, and I want you to really pay attention at this line, and that's how we delete a node from a linked list. So what we are saying, hey node, go ahead and dereference, access the field. So if you take a look at the node, the box that contains the variable node, it's pointing to the node that contains element 2. Go ahead and access that field and go to the next node, which is the node that contains element 3, and access the field down there, which is an address that points to the node that contains element 4, and take that address and assign it to the field that node, the pointer node, it's pointing to right now, which is the one that contains element 2. And that's how we delete the node that contains element 3. I want you to pay attention. You will see the node that contains element 3 disappear. And that's how we delete a node from a linked list. There it is. Now we go to the next line. We return, we go back to where the del node by position was called. And that's it. I think that would do it for this video. I hope you have a better understanding of how we add or insert or delete a node in the linked list, as well as how the compiler dynamically and uniquely allocates nodes in the memory. So if you have any questions, please let me know, and I will do my best to answer them. But for now, thank you for watching.